Hi everyone, my name is Hemant Reddy and we are presenting our project for Introduction to AI course, that is Connect for AI, comparing Minimax versus Q-Learning. We'll walk you through our approach, the algorithms and our findings. So our project main goal is to compare two classic AI approaches, that is Minimax AI versus Q-Learning, using the game Connect 4 basically. So, coming to the project overview, we implemented three types of AI players: Minmax with alpha beta pruning, so which is a classical search based algorithm, and Q learning, which is a reinforcement learning approach, and a normal player, which is basically uses simple rules. And we set up three game modes to see how these AI performs against each other. So basically, we can select from these three options, like which player you want, well, like which player versus which player you want to check out. And coming to project architecture, we have designed the project in a modular design where each approach has been in a different class. So basically, the board logic is in different class, a class are different classes, and the UI components are in different classes. And for visualization, we have basically used Pygame, which is basically used for designing games. And coming to the board implementation part, so basically the board class is the main logic of the game. Like it is using like 6 by 7 numpy array to represent the grid, which is efficient. And it checks for valid moves. First it checks for valid moves, then for, and also it detects for winds in all directions. It checks for legal moves, and as well as this class is being used by basically by all the AIs in common. And coming to normal player implementation, the normal player is basically designed to mimic beginner human player. Uh, the thing is, it first checks if it can win in the next move, or if it's not, it checks if it can block the threats that are posed by opponents from winning. And then if it isn't possible, it picks a random move. And then this is basically simple approach um, to which will be competing against Minmax and then Q learning. Coming to Minmax, so Minmax is basically a classical AI algorithm used in games like chess and tic-tac-toe, which works very effectively. And it works by simulating all possible moves upon to a certain depth and choosing the moves that leads to best outcome actually. And like as in, coming to the implementation part of the Minmax algorithm, so in our case, like our Minimax implementation, like is using a custom evaluation function. Basically, I will be showing it in the code. And basically, what we are doing is we are taking the control of the central column, like which will be very good, like statistically stronger in Connect 4 game. And then basically we are blocking the opponent's threats as well. And then like we have given our min max a search depth of 4. We have checked for different depths, and this found to be the optimal one. And as well as coming to min max strengths and limitations, min max is very strong in games like Connect 4 where the state space search is like manageable. And it's always plays optimally, giving enough search depth. If you have given the search depth enough, and it plays optimal. But the coming to the limitation part, it can be very slow. Like if you try to search too deeply, like in our case, we have opted for 4 depth, which is optimal in our case. But we have even tried with different one, which didn't work out. So coming to the coding part, let me show you the and explain the code first. So coming to board.py, so where the board class is basically the main logic lies in. So where we are using NumPy with an array of like using 6 by 7 grid, and then we are having basically some methods where the next move is where we are going where the we are placing the piece, and using there is a method called isMoveValid. So where we are checking if the move is valid or not. And then there is a method called getBlankRows, where we are having the next available row of column and this particular normal player. class. So this particular normal player class is where you'll be having where it will mimic like a human like strategy. So it basically has a single method in it, which is get move. Basically, where we are having is it basically works in three steps. So first it checks if it can win in the next move by simulating like each move, and then if it not, then it checks for the opponent can win in the next move, and then it blocks it. And if it's neither, it will pick a random move, valid move. And coming to this particular min-max class, so we are having a method for min-max where we are basically implementing min-max algorithm like with alpha beta pruning as well. So this particular min-max method, what it does is by it basically recursively calls itself and explores the possible moves like up to certain depth, where in our case we used 4. And uh, and we are also using this particular evaluation method, where basically we are saying that if we take this for center control, we are giving 4 as a reward, then for 2 3 4 we are giving some other rewards. And for blocking the threads, there will be a particular reward here as shown. And similarly, if we come to this particular q-learning class, so the q-learning class, we are basically implementing the q-learning algorithm. So we are maintaining this particular q table, and then saving it in this particular qtable.pkl file. Like we are using that particular table in this particular class. And so we are basically choosing an action method, which basically uses this part epsilon greedy strategy, like with the probability of epsilon. It basically explores a random move. So otherwise, like it chooses the best move from the known moves if from the particular table. And it's like the learning method basically it updates the q table using the Bellman equation as well. So and based on the reward and the like maximum future q value. And in this particular training q learning class is basically used where we are used for like to train like thousands of games against this particular min max and normal player. So for each episode, like the game like alternates between the this particular min max normal player and q agent. So rewards are given for the winning, losing, and drawing. So basically, training statistics will be like win, draw, lose rates, like for these particular 1 lakh episodes. At the end, the training Q table is saved like in this particular qtable.pkl file. And coming to main.py, this file like where we are providing some options to choose from the gaming modes, like whether you want to play min-max versus normal player, min-max versus q learning, etc. And then calling on the game the particular methods according to it. So let me run the code and show it to you like how it works. So if we run the code, it will be showing you 4 options to select: min-max versus normal pay. You want to select min-max versus Q learning versus normal pay, etc. So if you select this, it now for now I'm keeping it for two iterations. So now it's playing with a normal player. So min-max will obviously win. In the second iteration as well, so it's the min-max one. And now it asks us again to select an option like which player you want to play. From now, my teammate Nikesh will explain you about the Q-learning and Q-learning implementations.
Hello everyone, I am Nikesh and I'll be taking it from here. Q-learning is a type of reinforcement learning where the agent learns by playing game and receiving rewards or penalty. It doesn't need to know the rules of the game in advance. It learns by experience. The agent keeps a Q table, which is like a big spreadsheet mapping borders, states, and actions of expected rewards. Over the time, it learns which moves are good and which one are the bad. Moving to the next, Q-learning implementation. In our code, the Q-learning agent represent each board state as a string and stores Q values in our dictionary. It uses an Spleenian greed strategy. Most of times it picks the best known move, but sometimes it explores new moves. The learning rate and discount factor control, however, how quickly it learns and how much it values future rewards. We trained the agent for uh, more than 1,000 times games against the normal player, which took about 15 to 20 minutes. Moving to the next part, reward shaping and Q learning. One challenge in Connect 4 is that rewards are sparse. You only get a reward at the end of the game. To help the agent learn faster, we use reward shaping. For example, if the agent creates three in a row, uh, or it gives a small bonus. If it allows the opponent to create three in a row, it gets a penalty. This helps the agent learn which moves are promising, even if they don't immediately lead to a win. Moving on to the next one, it can the learning strengths and limitations. It can adapt. Firstly, it's a flexible learning is like very flexible thing. It can adapt to different opponents and even learn new strategies over the time. Very fast. It also very fast during gameplay, since it just look up the best moves in a queue table. However, it needs a lot of training, and if the training isn't diverse enough, it might not learn the best strategies. It also harder to understand why it makes certain moves compared to Minimax. Performance metrics, here are some numbers from our experiment. Minimax beats random about 95% of the time. Minimax beats Q learning about 70% of the time. Q learning beats normal player about 80% of the time. In terms of speed, Minimax takes about 100 to 500 milliseconds per move. Q learning takes less than 10 milliseconds, and normal player is even faster. Moving on to the next, conclusion and future works. In summary, Minimax is very strong in Connect 4, but Q Learning shows promises, especially as it gets more training. In the future, we could try using deep Q networks, which is a neural network, instead of a Q table, or tree search, which is used in programs like AlphaGo. We could also try training the Q learning agent by having it play by itself, which most of our new modern AIs are trained. So thank you everyone for listening. We are happy to take any questions. How could we approach the project? By using neural network, more advanced search algorithm, or by parallelizing the Minimax search. So that's, thank you.